Okay, this brings us to another thermal expansion situation here. Here, this is fairly straightforward. I have these two bars. One is made of aluminum, one is made of brass. Let's assume that the walls that they're attached to will not move, and there's a gap between them. The gap is labeled as X there. The initial lengths of the rods are known, so that will be initial for brass and initial for aluminum, and their coefficients are known as well. So coefficient for aluminum, coefficient for brass. At what temperature will the gap be closed? Okay, so here, what we know is that we want these to close into the gap. So we know that we're going to want to heat, right, the combination in order to have our length increase. They both have positive coefficients, so they both expand with increasing temperature. And if we want that gap, if we want them both to increase into the gap, x, then I know that an equation I can set up here is that x is equal to the change in the brass plus the change in the aluminum. That the sum of those two changes, I don't care, they don't have, it's not going to be half and half, right? Because they're going to expand at different rates with respect to temperature. But I know that the sum of those two expansions should fill in the gap X. Sure. So with that, we can know that, can flesh this out a little bit using our thermal expansion equations here. For brass, I have the coefficient for brass times the initial length of brass, delta T, plus coefficient for aluminum, initial length of aluminum, times delta T. Now, sometimes students will ask, why does the initial length of the thing matter? Like, why is that part of the delta? If all we're talking about is the change. And how I usually answer that is, you can think about this physically. You can consider, if you want, like cutting the rod up into tiny little pieces. A way to think about this is each little piece is going to expand, right? If you cut it up into, say, millimeter slices or centimeter slices, whatever, each little slice is going to expand a little bit. What that means is that the more material you have, the more expansion that material will experience, right? It'll experience a particular, like a length expansion per unit length. So the more length there is, the more expansion that can happen. So that's why that's a proportional part of that expression there. So the delta T's are the same. These two rods are in the same temperature environment, and we're just being asked here at what temperature the gap will be closed. So then all we need to do at this point then is solve for delta T, and then after delta, well, I guess you can do this in whatever order you want. You want to solve for the final temperature. So I know that taking from this equation here, I can solve for delta T. It's going to be equal to X over these two terms, alpha aluminum, aluminum. And T final is, of course, T initial plus whatever the change is. In this case, the change happens to be positive, so we have the expectation that this is all going to be positive in here. So T final is equal to T initial, which is given in the problem, plus our change, which we just figured out. X over alpha B, L initial B of the brass, and then alpha aluminum, initial length of the aluminum. So that is my final temperature.